Hello, everyone. Welcome to Astronomy on Tap. I am Dr. Cameron Hummels. I will be your MC for this evening's event. So thank you for joining us this Monday, February 28th, the final day of February before moving on into the spring. We have a wonderful program tonight with two esteemed academics who are going to teach us all about binary stars and black holes. It should be very exciting. Let's see, a couple of announcements. Our next event will be this coming Friday, actually. Kind of got bogged down and had several events happening simultaneously or very quickly back to back. So there will be a stargazing lecture without the stargazing because it's going to be over YouTube, but it will occur this Friday at 7 p.m. It will also be on binary stars, although on massive binary stars and the ways in which they evolve and evolve differently because of the interactions that they have with nearby black holes and other stellar neighbors. That will be given by Dr. Margaret Lazzarini on Friday at 7. And we'll have a long Q&A after that with a few different members from the astronomy department here at Caltech. So I encourage you guys to check that out. Our next Astronomy on Tap will be in 2 weeks' time, and I haven't yet settled on the speakers and the talks that are going to be given, but stay tuned. I'll announce that reasonably soon. And I think those are the main announcements that I have. So if this is your first time watching, a quick layout of the schedule for tonight's event. I'll finish up these announcements in just a moment, and then I'll bring on our two speakers for tonight. Each one will give a roughly 15-minute presentation on their research topic, either binary stars or black holes. And then we'll take questions from the audience for 5 to 10 minutes on each one. The way in which you'll interact with us is by submitting your questions through either the YouTube chat or the Facebook chat or the Twitter chat or whatever medium that you're watching it through. And I'll scout them out and pick out the most relevant, interesting ones and ask our speaker. So I encourage you to interact that way. And then after we deal with both of the talks from our speakers and Q&A for a little bit, that should take us to the end of the hour. And then we'll have pub trivia, because everyone likes pub trivia. Originally, these events were held in a bar, and so what's better than being in a bar and doing pub trivia? So all of our pub trivia questions are astronomy themed, and they have a way for you to actually interact and submit your answers, and those pop up here, and then we see how the audience is doing and whether or not they're getting things right or wrong or have really funny answers or something like that. Unfortunately, there are no prizes except knowledge itself, but they're fun nonetheless. So I encourage people to stick around and participate in that. And that'll take about 45 minutes to an hour after the presentations are done. Yeah, okay, so those are all my announcements. Can I bring our speakers on? Ilva and Ron, would you like to join me? Hey,
Hello.
Good to see you. Hey, Ron, nice to see you, sir.
Hello.
So are you guys here in Pasadena? Are you guys, I know with the pandemic, people can be wherever they need to be and work remotely. Are you guys in town or are you guys elsewhere?
In Pasadena, yeah.
In Pasadena. Excellent. Ron?
Yeah, I'm in Pasadena too. The bedroom I spent the entire pandemic in, so.
Yeah, I was in a studio apartment for the bulk of the pandemic that was quite small. I wish I had not been in quite such a small space. So I had to move recently because it was just too tight of quarters. But good. Well, I'm glad to hear things are well with you guys and that you're nearby. And since this is Astronomy on Tap, are either of you guys drinking a beverage of choice?
I currently am. I'm drinking a Belgium style ale called Triple. So It's a new Belgian collection.
Oh, excellent.
Spelled TRIPPEL.
Okay. Excellent.
Moving away from IPAs.
Yeah, that's probably for the best.
I'm not. I have no. I have a hazy.
Oh, that sounds nice. Hazies are pretty good. I just
Yeah.
realized I have to grab my beer. Oh.
He has to float through the universe to grab his beer from his
Okay.
background picture.
Oh yeah, I just flew through a nebula to get this beer. So I'm really excited because it's not even going to show up. Please show up. Don't have the green screen. Can I make this work? It's a Bell's beer. It's Hop Slam, which is a classic double IPA. Sorry, Ron, that you're getting out of the IPA. This is a really good beer, and I encourage people. It only comes out like once a year, and it's super solid. So I'm really looking forward to it. But I have to limit myself because it's like 10%. So this might
Yeah, I think mine's like 9% too.
might turn into a
somewhere around there.
On tap.
That's 8.5%.
Okay, so Ron, do you want to share your screen and we'll get started with your presentation on black holes?
Yeah, let me share. Keynote. Share.
Where is my spiel for you? Oh, here we are. Okay. Rondale, also known as Ron So, is a graduate student in the relativity group at Caltech. He works on creating models to test relativity and studies the interesting world of relativity and black holes. In addition to studying and researching relativistic effects in the universe, he enjoys history and exploring the world both in person and virtually. This summer, he will continue his academic career as a postdoctoral researcher within the relativity group at University of Illinois, Urbana-Champaign. So that's very exciting. You're finishing your PhD this spring.
Yeah. So I'm sort of working towards that. I'm in the process of writing my thesis. So I'm kind of sorry if I forget like specific stuff about astrophysics, like I knew during my candidacy exam. So I'm like all in this world of like, relativity and testing GR and like sort of
that's
what
we're excited to hear about. That's exciting. I look forward to being able to calling you Dr. Rondale so soon. So
that's definitely exciting. Definitely exciting. I think I'll allow people to call me that just once. I would rather go by name Ron for like the duration of like academia. It's so simple,
Yeah, that's true.
I like things simple.
Cool. Well, I'll let you take it away. Thanks, Ron.
All right. So my talk's on dancing black holes. It's sort of like is an artistic rendition in the background, sort of talking about this. It's not exactly accurate. I mean, it's artistic rendition. I'll show you one that's a little bit more accurate. So most of these images I'm going to show you, you can find it on the LIGO website. Like if you just Google LIGO, the first one that pops up, I think it's like called like ligo.caltech.edu. You go to the gallery and you can see all the all the recognition for who made these images. So I go by Ron. My full name is Rondale. So I'm a relativity group at Caltech. We'll jump into it. So this is sort of like an image I kind of like, you probably see this on like, documentaries on whatever the Science Channel or History Channel or whatever, covers this kind of a thing. They kind of talk about how, matter curves space-time and space-time tells where matter to move. And that's sort of like the description in Einstein's field equations. So right here you have like matter, which is like the sun and the moon. So it's sort of like, it's like an interplay between both of them. So you have like matter that sources like, like what we call the stress energy tensor of space-time, so it sort of like determines like how it stresses space-time around it and stuff like that, and creates this type of curvature. And essentially that sort of determines like how objects move around each other. So like an orbit can essentially be described by something like this. If you go on YouTube, you can find a lot of videos describing this with this like rubber sheet with like marbles and like a giant, like a shot put ball or something like that. And it's a nice, good demonstration. So talk about this orbital system. So dealing with black holes is that they're very compact and they're very heavy. They're very massive objects. And when they're orbiting each other, they're sort of causing like this sort of like reaction in space-time where they're orbiting each other, they're accelerating. So they cause rapid distortion in space-time, and space-time tries to correct itself for the most part. And that creates sort of this nonlinear system, in a binary dynamic. So right here is like a simulation, like this is the more realistic one. So you have two black holes that are orbiting each other, and the background sort of represents like the space-time and everything around it. So they're orbiting, the orbital decays, there's orbital decay going on because of the nonlinear features of relativity. So they start to inspiral, and at the bottom you sort of see the waveform. So it's kind of like in the late inspiral phase right here. So you interpret that as that. And if you look in the top left corner, this is actually happening all in a fraction of a second. So they go ahead and they come together. And the final stage becomes in this merger event, and you'll see the video sort of slow down very quickly to sort of like depict this. It's like a nice little action shot that goes on. And eventually they merge into one final black hole that's essentially excited, I guess you can describe it as. It's sort of like a type of excitation stage it goes through. And it goes through this ring down phase. And what's like produced is this waveform. So it'll zoom out and it'll show the entire stage of the waveform going in. So that's a signal essentially being emitted in space-time right there. Those very strong ones, the merger signal, and then you have the ring down signal. So it's going out. So we first see the inspiral stage, first see the merger, and then we see the ring down kind of a thing, because that's how we get the information from it. So most of my work has been done in testing relativity. There's a variety of ways of testing relativity. One is you can do a direct test, of relativity, like so you sort of do like consider like some alternative theory and do like a test associated with that. You can also do what we call internal consistency tests. And this has been done like since the beginning of the time. Like there's Mercury's orbital precession that general relativity sort of like took into account. But that was sort of just like a confirmation in a way, to be like, oh, this actually can explain it. It's not a direct test of relativity. And then you also have the light deflection, light bending. And this first panel over here sort of describes that, sort of the experiments that have been going on, for like 100 years or something. You have like the light deflection that's been going on caused by the sun. So the first one is like the optical one, and those error bars at the beginning, those are massive error bars. Like those wouldn't pass in today's like world of astronomy. But as you get further on, it becomes very more precise. Like right there is like a 10 to the -4 fraction of a constraint. In the middle, like we also have like something called gravitational redshift. That's what this kind of like this delta nu over nu, this frequency test type of a experiment that goes on. And eventually we have gravitational radiation, which is the era we're in. And there was an indirect confirmation, which was sort of the orbital decay of two binary neutron stars that were orbiting together, and sort of like we're able to detect, the geometric makeup of that of those two pulse. Has to be pulsars, yeah. Two pulsars, sort of decaying together. And we're sort of plotting that decay is like, and we look at the general theory prediction, general relativity prediction, like those line up precisely. So that's like the first indirect detection of gravitational waves. And of course, everyone's favorite 1509-14 that was observed like how long ago has it been? Like 7 years, 7 years. So this is like the Hanford LIGO detector, the LIGO Livingston detector, and sort of the combination of those. And it says shifted there because you had to do some like translation because they're separated. And according to relativity, these gravitational waves travel at the speed of light. So you just have to shift it, relative to what the speed of light, like in their separation, would be based on what direction it comes, and the overlies, but like it lies over each other just very nicely like that. And this is the actual detection and everything. And that got everyone excited. And that's just the first detection. And I believe this is the most up-to-date one. So in the blue are all the detections made by the LIGO Virgo Kyra, collaborations. And then we've also seen the neutron stars also detected by those collaborations, which are these orange ones at the bottom right here. The x-axis here doesn't really explain anything, so it's just like for visual design and everything. And then like the y-axis here is just talking about what solar masses it was, and the errors are sort of like little gray errors are showing them is saying showing like what they merged to. And if you see some of them for the neutron stars, like they're not entirely sure if they formed a black hole or not. Maybe it's a heavy neutron star, maybe it's a very light black hole. So that's still uncertain. And of course, you have all the detections that were made by astronomers, which are the E and M black holes and the E and M neutron stars down there. We call this the masses in the stellar graveyard, essentially. So in most of these, for the most part, have been understood to be caused by long-lived binaries. So like, these two stars, they do this dance at the very beginning. There are these massive stars and everything, and then one dies out and the other one astrophysically gets sad, and then also meets its other partner. So they kind of, even in death, they're still dancing together. So it's like they find this, they form this final black hole, eventually, they coalesce as one again. So that's how it goes for the most part. And some of the more heavier ones that have been formed, we're not entirely sure exactly how they formed. Because like they're sort of like very massive stars, and there's this thing in the supernova process called, I'll say the word, it's called the pair instability process, which says that these very large black holes probably should not exist in this intermediate mass range kind of a thing. And one explanation, this is a later event in 2019, is there a possibility of three body dynamics going on? Like, maybe this occurred like, with two other, stellar mass black holes that sort of like coalesce together. And eventually at the end, those two find each other again and they form together. And you have this sort of dynamical formation process that goes on. And there's sort of like another process that's kind of interests me, for the most part. It's also, instead of like thinking about these two that form together, or I guess like four that form together to form two and two forms one kind of a thing, this hierarchical process. One was looking at this process called of three body systems. And essentially what you have is an inner binary, which are the two black holes on the left. I guess that's the inner binary there. That's like describing two stellar mass black hole. And at the very end, you have this black hole that's very far away that's orbiting it. It can perturb its orbit. And you can have a lot of like interesting effects that go on in this. And one of them is the Kozai, what they call the Kozai-Lidov oscillations, which I won't go too much in, but the rundown of it is essentially there's sort of like a resonant frequency between the inner binary and the outer binary kind of a thing. And it's exchanging the eccentricity of the inner and outer binary it's just exchanging the eccentricity of the inner binary with the inclination of the outer binary with respect to the inner binary. It's a very complicated process, so that's why I really don't want to get too in depth with it. And one thing I've been interested in is like, the radiation reaction effects, the process of exciting, sort of these additional what we call multiple moments that will, sort of like disrupt the orbital dynamics of the entire system. And an interesting prospect that we've been looking into is how it causes that ring down excitation. Remember, I told you at the end when the final black hole forms, it's like sort of this excited state where there's excited, according to what we call the no hair theorem, they should be radiating away these things. So it goes into a nice relaxed state. Black holes don't like to be very excited. They like to be lazy and sort of just like be relaxed. And this is sort of like an overview of like what we hope to see in the future. So we see the red curve is advanced LIGO at the design stage. In the future, in the purple, we hope to have like A+. And then what I'm also being a part of is the CE consortium, which is called the CE stands for Cosmic Explorer. That's that brown one right there. That's the third generation detector that the US is hoping to build. It's essentially like making LIGO but bigger. And in the decihertz range, we have these like these dream projects like this Tiango one, initial Tiango, advanced Tiango, which are the blue and orange curves. And then we have Desigo, which is the green one, which is like the most optimal thing that some of us would like to have, especially when you're dealing with three body systems, because all of those hierarchical processes that occur, whether it's just like you have some hierarchical system process or you have a three body system. So you have like a more complicated dancing process of these black holes, that decihertz range, as we call them, the two Tiangos and the Desigo, the Tiango actually kind of like matches with this. So those two, like those occur in what we call the decihertz range, whereas like these ground-based detectors, they're limited by the seismic noise, I guess, of Earth. So that's why they can't go below like 10 hertz. So they exist in what we call the kilohertz range. And this is an example of just like the signal noise ratios, which is essentially describing how loud it is with respect to each, signal. It also can tell us like, the number of binaries that we can observe within a given year and everything. The log uniform power law are just like mass distributions. I won't really get too much into that. As you can see, Desigo is the loudest. And then you can see like Cosmic Explorer is the next loudest, which is the one like Desigo is sort of like a pipe dream, I guess you could sort of think of it. It's like the ideal, it's like what we would want, but it's kind of like most likely we won't be able to get it, but we can work towards it. And Cosmic Explorer, we hope to have it up in the 2030s, around the time the laser interferometer space antenna gets launched, and that's looking in the millihertz range. So that's like below frequency range than things like Desigo and stuff like that. and the two Tiangos. And we go down, and I talked about this process of the ring down stage. And so the whole process of like during the end spiral stage of like the whole process of like, you know, you have the three body system, as I mentioned earlier, you know, that whole process that's going on right there. It's like that sort of like affects the dynamics. You have Kozai-Litov oscillations. I have some other ideas that, you know, I'm sort of probing still. There's sort of like additional nonlinear features that can sort of like cause excitations just in the orbital dynamics, not in the ring down stage yet, because the inner binary has not ring down. So, and then like so like that excitation can cause like this three body system to essentially merge together in a type of like within what we call a Hubble time. Hubble time is like some fraction of the age of the universe, I guess. So it's like sometimes you do some calculation, like, you know, you'll be like, oh, this is a really great idea, I hope this will work. And like a lot of us theorists like to do that. But at the end of the day, it comes down to like, you know, just sort of just doing like you know, like doing realistic calculations, looking at time scale estimates and things like that. Because a lot of times, like you have a really great idea, you think it's the greatest thing ever, and like your great idea just dies on paper because like it'll like, you know, observing these effects take like 5 times the age of the universe, which is unrealistic. So that's the whole process dealing with these. And with this ring down stage, like I mentioned, it's like they call them bumpy black holes, but it's not really a bumpy black hole as a lot of these things sort of describe it as. It's sort of like excited black hole is the best description I can sort of describe it as. And it's, you can, in this ring down stage, you can sort of like, I've heard a lot of analogies. It's like, you know, when you like tap the side of a bell and you have that ringing sound, and that ringing sound has additional, different modes associated with it. You have like the dominant mode, the one your ear picks up at, and then like, you know, you can look at higher, you know, like at different frequencies and stuff like that. You can see like subdominant modes. And essentially, like infinitely number of them describe the final ring down signal, I guess. And you can sort of describe, you know, from based on like the frequency and time scale and stuff like that, you can estimate what the final mass and spin is, because everything about a black hole should be described by the mass and the spin of a black hole. That's what's known as a no-hair theorem for the most part. So this is sort of like if you have a third body orbiting around it, like, is it possible to excite, you know, additional multipole terms that create like an interesting signal in some of these subdominant modes or something, or maybe there's something else that's causing some additional excitation in there. So that's essentially like what I hope to look at, in addition to like my other projects and like finding ways to test relativity with like, you know, some alternative theory. This one's more of like an internal consistency test, sort of just looking at what we call the nonlinear effects of general relativity, which is something really nice to look at. So today, up to today, GR has passed all existing tests, you know, with flying colors, I think is the description that's given to it. And for the most part, like with the future looks bright in terms of gravitational wave astronomy. So it's a great time to develop and implement models for the next generation, you know, for the second, like for 2.5 generation, we call it, and the third generation. So currently we'll continue to, you know, to extend this current work, especially the three body systems and formation. Also, additionally, this radiation reaction effects that I talked about. I think I talked about them. I might have mentioned them. That's the thing that's essentially causing the three body system to cause additional excitation modes. You have this was what they call radiation reaction effects for the most part. And so yeah, so this is the conclusion of the slide. And this is acknowledgements for the most part that was supported by a multiple of fellowships. These guys, you know, kept me fed. Also got to go and be in Copenhagen for a bit back in 2017, like where I did some of these rates analysis and things like that. So yeah, I'm really excited, you know, to be continuing to work at the University of Illinois Urbana-Champaign with Diku Yunus in his relativity group. And I guess like we'll go to questions.
Thanks, Ron. A lot of stuff there. So we encourage people to ask questions in the, you know, YouTube chat or the Twitter chat or the Facebook chat, whichever medium you're using. We already have a few questions from our audience. One is kind of a fundamental question that I think is really important for understanding the results you were discussing, and that is, what is gravitational radiation? The example was like, is it like alpha or beta or gamma radiation in terms of the particles that are emitted by the electroweak or the weak nuclear processes, or is it something totally different?
Yeah, it can be described in sort of like in both ways. You have like the particle perspective of it. We have what we call the graviton, in which the graviton has never been observed because the graviton, the particle aspect of the graviton is so very weakly interacting that, and all you can see is the bulk motion of the effects of the graviton. So the first gravitational wave event had some crazy number like 10 to the 40, 10 to the 50 gravitons. So you're not seeing the particle or quantum description of gravity in that sense. You're seeing its classical description because there's so many, you know. And then the other aspect on the classical side is what it is. Gravitational radiation is oscillations in space-time itself. So when I mentioned that the gravitational waves were being emitted in that process, like it's like space-time correcting itself. So it correcting itself is what radiates away. So it's like the oscillations in space-time itself. So that's the classical description.
So it's oscillations in space-time itself, but for us on the ground, that would actually be like a warping of the dimension of space in front of us. Like it's a stretching or a straining of that space, and that's how LIGO or COGRA or any of these gravitational wave detectors work, is by monitoring how much that stretches, even by a minuscule amount. Correct.
So I guess if you see like a gravitational wave going in this direction, is what we call a transverse wave, is that the oscillation goes in this direction. So the space time, the space, I guess I'll stop saying this time or something, because like what we're measuring is space oscillations. It's going along in the direction of my hand. That's where you're seeing the oscillation occurring. It's like that's how space is oscillating, and it's going in this direction. So that's just the description of that.
I see. A few other questions from the audience. Andrew Reidemeyer asks, if two separate merger events from merging black holes, as you described, if you have a merger that's happening over here and a merger that's happening over here per se, and they're each causing these gravitational wave disturbances that are traveling out, and say we sit here, would you be able to, if both of those kind of disturbances of gravitational waves reached us, the observer, at the same time, would you be able to observe interference patterns in the way that we can observe interference patterns from electromagnetic radiation events from two separate sources that kind of coincide in their waveforms?
I think for the most part, it's very difficult. Like, yes, that physically that should occur. But the problem is that your gravitational waves are not like a concentrated beam in the sense like the way light is. It kind of goes out all direction, very weakly interacting kind of a thing. So like you would see that effect if something was a little bit more concentrated, like you see like light and everything, you see some diffraction pattern that occurs. If gravitational waves are just not like that. I know in the past, like people talked about seeing gravitational waves in like stellar oscillations and things like that. Like if the gravitational wave impacts a star, you would definitely see like they talk about like, yeah, technically you should see an oscillation in the star, but it's such a weak signal at that point. I mean, like there's that thing like the gravitational waves, like the detectors we have is just like a very small. It's like 1/1000th. The oscillations is like 1/1000th the size of a proton. I think the number is. I think that's the number is. So don't quote me completely on that, but it's a very small size. The size of a proton, and that's with a very sensitive detectors that we use. So like seeing this effect or just seeing the scattering effect is like very unlikely. And there's some stuff that people talk about measuring effects of with what we call gravitational lensing, that light bending effect, seeing that effect with gravitational waves.
Interesting. So, I mean, because gravitational waves are waves, presumably they will have like diffraction if they go around some sort of boundary condition, in the same way that you can have like water waves traveling, and then if they go around some sort of boundary in that, they'll diffract out or that sort of thing. It's interesting to think about. Obviously, we don't really have the sensitivity to pick that up because we only have a handful of gravitational wave detectors at present. But I guess perhaps in the future we'll be able to pick up these sorts of kind of minute effects. But
ideally, maybe there's some Yeah, I mean, like, but yeah, it's like for the most part, and like in physics, you sort of just look at the first order effects and you try to measure those.
Sure.
Yeah.
Interesting. Very interesting. There is a question here from Hong Du who says, if black holes can bend light, then why are they black if they're bending light around them?
Well, because it essentially comes down to when a star collapses and everything, it reaches like sort of a density where light gets infinitely redshifted. Because that's the thing. Like I think I mentioned previously in the slides. Let me see if I can find it really quick. Don't want to take too much time. Like this whole idea of gravitational redshift, like they can measure that on Earth, the gravitational redshift effect. It's due to like a massive object. So if you have something as dense as like a black hole, something as dense and massive as a black hole, right? Essentially what's happening is that light gets closer and light's being emitted closer and closer to the black hole, it gets redshifted. So at the surface of the black hole, it gets infinitely redshifted. So the light just can't escape it. So
Indeed. That's a good explanation. Let's see. Other questions. So I had a question. So you were talking about, instruments that are going to be coming online, and how those might contribute to these sorts of studies. So right now you're studying the effects of GR as it pertains to black holes. Are there other environments where you can, that as other instruments come online, you might be able to study the effects of gravitation or of GR in some of these extreme environments that aren't just around black holes, perhaps other environments that might also be good test beds for this sort of thing?
Yeah, yes, definitely, for sure. I mean, the earliest test beds was right here. This famous publications by Cliff Will and everything. And he made his career out of testing relativity, and it's all based on solar system constraints, doing
Okay.
tests within the solar system. And there's like, a lot of cosmologists who do this like on a more cosmological scale and everything, not just dealing with like black holes and binary dynamics and things like that.
Excellent. One last question, and that is from Stephen Schreier. Hypothetically, could an advanced LIGO detector detect a black hole merger from beyond the edge of the visible universe?
Not a LIGO detector, because eventually, as you get down to third generation detectors, you're going to hit this level of what we call a stochastic background, of where all the binary mergers in the age of the universe, like not in the age of the universe, that we can observe or something, you're going to start observing all of them. So it's kind of like when we see what we call the cosmic microwave background radiation, you're going to hit a background of all these signals and everything to the point where you can't see beyond it. There have been proposals. This is kind of like what they do with was it Bicep 2, was it? I'm not sure if you remember, Cameron, but they look at the CMB, and they look for some of these E and B modes, I believe, which like look at potential like gravitational wave events at the beginning of the universe.
That's right. That's perfect.
Yeah.
I think the real hang up is we can't. Gravitational waves also travel at the same speed of light that electromagnetic waves travel at. So we're still stymied by the edge of the visible universe, and gravitational waves won't be able to get past that boundary, just as electromagnetic waves. For additional reasons. But as you say, like, there's that stochastic background that makes it impossible to even see to that edge for the same reason. So
yeah, and there's definitely still some segments of the universe that we're causally disconnected from currently because of rapid inflation. That boggles my mind. Like,
it's true. It boggles mine too. Excellent. Well, thank you very much, Ron. That was an excellent talk, and I learned a bunch of things. Thank you. Oh, Ilva, you're here. Excellent. So do you want to share your screen and I'll give you your introduction?
Sure. I don't know.
Okay, great. So we'll move, just so our audience is keeping up, we'll move from black holes and general relativity over to binary stars in the universe and in computers as well. So I'm going to try and get this correct. Dr. Ilva Yotbari is a postdoctoral researcher in theoretical and observational astrophysics at the Carnegie Observatories here in Pasadena, the same place where Edwin Hubble, the famous Edwin Hubble, and many other prominent astronomers have done their work in the last 100 years. Ylva's main research focus is in interacting binary stars. She makes simulations for mass exchange between the stars in double systems, and also observes binary stars after their mass exchange, after they've transferred mass between the two. And that's finished using the Magellan telescopes that are located in Chile in South America. Ylva also likes to travel. She likes to hike in the outdoors and to try new food. Oh, I like trying new food. I also like hiking. I like all of those things. I like binary stars too. So I'm very excited for your presentation, Ylva.
Well, thank you so much, Cameron. Okay, so today I will take you through a little journey, a story about how we found a certain type of stars. I work with interacting binary stars, something you can see in the background here, interaction going on. And we're going to start from the computer, go to the universe, and then back again. Okay, so these pictures, maybe you think, oh, is that a computer? Is that the universe? And I am aware that I picked maybe quite a big computer, not so usual, but this is what we usually use, and an interpretation of the universe where you can see far out in cosmic time, which I also like to think about because binary stars can affect all these different stages in the evolution of the universe. So in this story about how we found a certain type of star, let's begin with how do you actually discover what there is in the universe? What is usually done? So you can either study some random stuff that occurs in the sky, or you can look for some specific things. So let's look at these two categories and think about how have people worked with these before. So for example, comets, they randomly occurred in the sky. Here you can see an image from the Codex Duran where the king of the Aztecs observed the Halley comet. And these kind of objects tended to be a little bit poorly understood to begin with, but now we know much more. It includes also explosions of stars, supernovae, pulsars, which is these kind of cosmic lighthouses. I mean, who would have known that the universe has lighthouses? So this is just some random stuff that was detected. There is also the so-called fast radio bursts. These are little blips of radio radiation that just occurs to us, and we don't yet know what they are. And maybe it's something that you heard of that is like really weird that we don't understand yet. Is dark matter, no? What is it? But we have seen that there is too much matter compared to what is visible in the universe. So these are things that we now understand better, but there could also be lots of things that we yet have to understand. There's also some things that were predicted that has been detected, like exoplanets, for example. It makes sense. There is the planets around the sun. Why shouldn't there be planets around other stars? But something really remarkable, I think, that was predicted and then detected is, for example, the black holes that Ron was just talking about, which with the theory of Einstein came as well, the gravitational lensing, that you can see the same object here lensed 4 times. You can see the same galaxy around this galaxy cluster, or gravitational waves, where here you can see the artist's impression of 2 neutron stars spiraling closer and closer together. And these 4 things have now been detected, for example. And I mean, now maybe you hope that I'm going to put in here, as I also hope, on the right-hand side, aliens. I mean, I wish I would also have discovered aliens, but no, I'm going to put here instead a certain type of star made of almost only helium. So I work with stars. This is an image of Westerlund 1, which is a massive star cluster located in the Milky Way. And stars are made mostly of hydrogen and helium, and I'm going to show you how we found these stars made almost only of helium. And to begin, well, I think we should mention that it has not always been very well known that stars are composed of hydrogen and helium. This is a quote from a very famous astronomer, Henry Norris Russell, in 1914, when he says that if the Earth's crust should be raised to the temperature of the sun's atmosphere, it would give a very similar absorption spectrum. The spectra of the sun and other stars were similar, so it appeared that the relative abundance of elements in the universe was like that in the Earth's crust. So what Henry Norris Russell said in 1914 was that basically he thinks that the stars are made of the same elements as the Earth. Now we know that this is not true, and that discovery was made by Cecilia Payne-Gaposchkin in her PhD thesis, where she studied the atmospheres of the stars and found that they mostly contain hydrogen and helium. It's quite modestly phrased in her PhD thesis, because Henry Norris Russell did not like this discovery. He didn't believe in it. So therefore, she says this is probably not true. But later on, this was proven again to be true. So now, what is to really go to those helium stars, to those helium balls, we need to better understand what is a star, but really, what does a star do? So I would claim here that stars are factories in the universe. They are factories of elements. Stars create elements. And so to understand how this is happening, we need to look a little bit into the physics. So imagine this is a star, a young star. It's made up mostly of hydrogen and helium. In the center, the conditions are such that the temperature is so hot that nuclear fusion can occur, and hydrogen is fused to helium. So this star is creating helium. This nuclear process is giving energy. So actually it's radiated away as photons, and this is propagating through the star, resulting in photons being emitted from the star. This is why the stars are shining. Eventually, in the central region here, the hydrogen is going to be depleted, and there is only going to be helium. So eventually, the star has created this helium core, and as you could notice here from the image, the star also expanded. The nuclear fusion can later continue fusing helium further to carbon and oxygen, but I'm going to stop and show you only these two evolutionary phases of a massive star, where you can see first we have the first stage called the main sequence star, when hydrogen is fusing to helium in the core, and then the second stage where you have this helium core created in the center. So there is two important processes to keep in mind here. There is this creation of a helium core, and the second, that we have that radial expansion. Now you might have an idea of where I'm going with this, because we have this helium core created. Maybe that can be exposed somehow. And I would show you that this can be exposed through interaction in a binary. And so this artist's impression here shows you two stars orbiting each other in a binary system, double star system. And one of these stars is most massive, so it's going to burn through its fuel much faster. It has much higher temperature in the center, and therefore it's going to expand first. And it's this white star that you can see is now growing and growing. And what eventually is going to happen is that the outer layers there, oh, look at that, are going to be transferred from the one star to the other star. As you can see, this mass transfer process, it occurs until there is very little of that envelope left. It's completely gone. And at that stage, you can see that helium core of the star. It is, so to say, a star stripped of its envelope, a stripped star, a helium star. I may use this a little bit interchangeably. So I want to mention that even though this was an artist's impression, there is one star where we have been able to see actually this ongoing mass transfer phase, and it is Beta Lyra. Beta Lyra is a massive system where the donor star, the star that is losing its envelope, is 3 solar masses, and the accretor star is 13 solar masses. So much of the 13 solar masses comes from the envelope of that donor star. Here you can see this is actual images. They are taken with the Chara array, which is actually really nearby. I took this picture today for you to see, so you may recognize the Colorado here. And this is outside on the street, where you can see up here on the mountain, there is Mount Wilson, and the Chara array is located there. The Chara array is a large interferometer, so you can actually resolve the 2 stars in the binary. And you can see that the donor star, the dark star here, is deformed, transferring material to the companion star. So looking closer at this, we had 2 stars in the binary. They orbit each other. The most massive star, it creates that helium core. It starts to expand, but the outer layers feel strong gravitational force to the second star, being stripped off, and you expose that helium core. So let's, now these helium stars, you may be like, yes, that she says it's a helium star, never heard about that before. What is it really? Is it important? So let's compare a little bit. A regular star, like the sun, maybe has a surface temperature of 3,000 to 30,000 Kelvin. Sun specifically has about 6,000 Kelvin, whereas the helium star is much, much hotter. It's that compact core of the progenitor star, 30 to 100,000 Kelvin more light gas. The regular star is hydrogen rich, but the helium star is helium rich and hydrogen poor, right? We don't have that envelope anymore. And the regular star is relatively large and fluffy, whilst the helium star is very compact. So now to mention the regular stars, as you may know, when you look up in the skies, they are very, very common. Helium stars, we have only found 1. Now that is a problem. And why is that a problem, you may ask? So that now I'm very happy that Ron already talked a bit about the gravitational waves, for example, because I think that this is one of the best arguments for why helium stars are really relevant to learn more about and understand better. Because in the case of these 2 neutron stars spiraling closer together, eventually merging in that gravitational wave event where you see this ripple of the space-time propagating outwards, to get those 2 neutron stars so close to each other, you need not just 1 envelope stripping phase, but 2. Here, it's quite complicated chart, but you may recognize this mass transfer phase here resulting in this stripped helium star. And there is another one over here where the second star is stripped as well. So to better understand, for example, the creation of merging neutron stars, we need to better understand these interaction products of binaries. So how do we go about this? How do we find these helium stars? How do you find something that has not been found before? This is a video showing you one of the most common techniques where we're going to sort the stars in terms of temperature, where the blue, the hot stars, are going to go to the left, and the red, the cool stars, go to the right. And then we're going to sort this in terms of brightness, with the bright stars at the top and the cool stars at the bottom. And now when this is done, you can see that quite a nice sequence of the stars in the stellar population has been created. And this main one here is called the main sequence. Well, you have some giants here, red giants, red supergiants, some blue giants, and here you have some really faint blue stars like subdwarfs or maybe even white dwarfs on here. So this diagram is known as the Hertzsprung-Russell diagram, coming back from Henry Norris Russell that I mentioned in the beginning. He also helped creating this diagram Where you have temperature, color is a good proxy for temperature, where red is cool, blue is hot, and brightness on the top here. And we expect that the stripped stars, the helium stars, should be very hot because they are the compact helium cores of their progenitors. So located here somewhere, but not super bright, in between. So color, a good proxy for temperature. And the stripped stars are so hot that we actually need to use UV colors and not just the regular visual colors that we can see with our eyes. So this is a survey that I've been doing together with my two collaborators, and where you can recognize here this main sequence. And this is now an actual diagram with stars here that we made, where you can see that sequence is the same. And therefore here we have candidate stars. And this is for another galaxy where we also did the same thing. So now we need to look closer at all of these candidate stars to confirm that they are indeed such stripped stars. How we did that, we looked at, we split their light in terms of energy or wavelength, and looked, as you can see here, if you look in this box, you can see that there's all these wiggles going on. And it's basically like a barcode that you can use to recognize what kind of star it is. So just to show you a bit of actual real data that we took with this telescope down in Chile here. This is now that barcode for one of those helium stars. And some features here, these features are created by ionized helium. So it requires really high temperature to ionize the helium. And the helium is there because there is a lot of helium on the surface. This particular star also had a tiny bit of hydrogen left, so you can see a bit of contribution of hydrogen in these features. And there is highly ionized nitrogen. This is nitrogen of the ion of nitrogen that has lost, let's see, 4 electrons. So it's very hot, the surface of this star. And we can use these different features to determine the helium content and the temperature of the star. And so we did this for all of the stars in the sample and tried to place it in this diagram where we have temperature on the horizontal axis and the amount of helium on the vertical axis. So regular stars are located somewhere here, whilst the helium stars should be up there. And with our barcodes, our observations, that is where we end up with the stars in our sample. So I think that is pretty convincing that these indeed are helium stars. And at the moment, we are looking for the orbital motion to confirm they are actually also binary stars. And it looks really promising. So I hope that more people will be excited about these helium stars, and that we can do a lot of nice things with the interiors of stars with that. And I think they're really interesting for many things in the universe. So now I see I'm over time. So in case you have any questions, I'd be happy to answer.
Excellent presentation, Ylva. Thank you very much. That was super interesting.
Nice, I'm happy.
So these helium stars, I mean, white dwarfs, when they slough off their outer layers, can leave just that naked core as well. Are there really easy ways of discerning between that sort of thing and extracting the surface layers in this binary interaction?
Right. So Cameron is talking about.
Sorry, I jumped into that a little advanced. Thank you for introducing it. I don't.
Yeah.
Jump
No worries. A really young white dwarf, so it's still bright. It hasn't cooled yet.
Oh, I just ended your slide so that we could see your face more easily. That's all.
Thank you. I was like, did I get kicked out? Yes. Okay. So it's still a really bright and hot white dwarf. And sometimes they have many different names, but let's think of them as hot, bright white dwarfs. So many of those are actually exposed even further down the carbon and oxygen layers. You may see carbon and oxygen lines, which is not very common for exposed helium burning cores. But indeed, it has been a trick to confirm that these are not that type of objects. And I think the most promising ones are the two bright ones. That's the easiest to confirm that they are indeed not some rapid phase of a pre-white dwarf. But what you can see also is that the stars in our sample look similar, and that would infer that they tend to be the similar type of object. They are also nitrogen enriched, which is not very common for white dwarfs. And this comes from the nuclear fusion process that massive stars go through when they burn hydrogen to helium. They tend to enhance nitrogen a little bit, which does not happen in low mass stars that produce white dwarfs. But I am interested in the white dwarfs and pre-white dwarfs as well. I think that they are really cool and can produce a lot of ionizing radiation as well.
Yes.
Lots of fun things.
Yes. Excellent. Okay, so yeah, I encourage people to ask questions. We already have a couple in the chat, but feel free to write them in the various different comment sections of the medium that you're watching this through. Andrew Reitemeyer asks, will the James Webb Space Telescope will it enable the discovery of more of these types of helium stars like what you were discussing tonight?
Oh, that's a very good question. So the James Webb Space Telescope is a telescope that targets primarily infrared radiation and more low energetic radiation compared to what is the peak radiation of helium stars. Remember, helium stars are really hot, and therefore they emit most of the radiation in the ionizing regime, which is really, really energetic. So this is a little bit hard for the James Webb to look at, but there is two things that I can mention that would be interesting. So first, infrared radiation is really good to observe because it goes through a lot of dust and gas and things like that. So you may be able to see stars in obscured regions. And actually, they tend to have quite some of those features in that part of the wavelength range. So if indeed it would be sufficiently nearby and the stars are bright enough, this could be an advantageous point. Also, you can see far in the universe, because the light from the distant universe redshifts. And so some really hot, highly energetic radiation can redshift to the infrared bands if you look sufficiently far away. Then maybe you will not be able to see individual stars, but what you could see is the effect of the individual stars. For example, if you have a large population of this, which is the prediction, you may be able to see ionizing effects, for example, or even stellar features in the composite spectrum of a galaxy, for example.
We think that there will be more of these. You said it's a prediction to find a larger population of these. Do we tend to find those in galaxies that formed or existed in earlier periods of the universe? We'd find more of these multiple star systems that could lead to these helium stars?
It's a hard question, just because you cannot observe individual stars in such distant galaxies. But if you look, for example, at galaxies that are more nearby with similar chemical compositions, you do see binary stars and tight binary stars, and it is predicted that they should interact and create these helium stars. Now, I showed you the largest sample of helium stars there is at this moment, and they happen to come from the nearby galaxies that are really close. So hopefully we can extend to even different metal compositions and make stronger claims for the early universe. But yeah, I would say, why wouldn't there be binaries in the early universe?
That's a good question. I don't know. Let's find out. Let's find out. Matt Brorby asks, you showed a diagram of the different phases binaries can go through throughout their evolution. How long lived is the bare helium star phase that near the end of its life compared to the other phases? Is it a short period? Is it a long period? And thus kind of a consequent question is, so how many of these helium binaries are predicted to exist, given we know about their kind of the long-livedness of that particular phase of their evolution?
Yeah, I apologize for skipping through that very quickly.
Okay. I forgive you.
Thank you. So the regular star phase, where you have hydrogen fusion going on in the center, that corresponds to roughly 90% of the stellar lifetime. And the helium core burning phase, where you have helium fusion, where the star can be stripped, corresponds to roughly 10% of the stellar lifetime. So with the predictions from how tight binaries are, how common it is that interactions should occur and mass transfer to occur, we think that about 3 to 5% of all massive stars should at this moment have a stripped companion. That corresponds to, for the Milky Way, many thousands of stripped stars present at this moment. We just have not seen them yet. And there's one. I should mention there is one. But we have not seen the thousands of the populations. We have not mapped it out. So this is something still yet to be confirmed. And if it is that they do not exist, we have a problem with, for example, the creation of merging binary neutron stars or hydrogen poor stellar explosions, for example. So much left to do, I would say.
Excellent. Well, thank you for your presentation and for your great explanations. Very much appreciated.
Thank you.
Okay, so with those two presentations down, we will move on to, oh, you guys can both come back on. You don't have to disappear, Ron and Ylva. We'll move on to the portion of the night that is astronomy themed pub trivia for all of you guys to participate in. You guys included our speakers for tonight, but no pressure. Let's see. So what we're going to do is, everybody likes trivia, right? Everyone likes to kind of compete with each other in some manner in questions and knowledge of stuff that might not have that much application in the real world. It's just kind of trivial information, but it's still interesting nonetheless. So let me share my screen for this. Here we are. Oops. Okay, so can everyone see that screen? Ylva and Ron, can you guys see this okay?
Yeah.
Okay. Great. So our viewers, I encourage you to go to this website that's listed at the top, menti.com, and then typing in this specific code. Don't worry, you're not going to get charged. You're not going to get spammed. Your email's not going to get spammed. This is just open it up in another browser, either on your phone or on your computer in a different browser window or tab. And what will happen is the questions will pop up on your screen, and then you can type in an answer, and then we'll get the results of what everyone is answering. And so we can all see how well everyone does. It's just some layer of interactivity in this world of post-COVID lack of interaction with each other. This allows some level of interaction, but no, there's nothing that will obligate you to anything. No cookies that are even sent to your browser. Like it's just, this is just for fun. So don't stress about it too much. And the other thing that I should mention is there's no reason to cheat here because there's no prize, unfortunately. But I encourage everybody to just write down an answer. It can be wrong. It can be goofy if you don't know the answer. Write down something silly or whatever. We're just looking for participation from everyone. But maybe you'll know the answer too. So, and some of these you can kind of figure out. You can reason and figure them out. So the first question is, last week, the James Webb Space Telescope did what? It made a major milestone in its kind of progress towards taking scientific data. You'll recall that the James Webb Space Telescope, so feel free to type in whatever answer that you might have into that browser if you have it open. But yeah, the James Webb Space Telescope launched on Christmas morning just a couple of months ago, and now it's in the process of getting ready to be taking science data. So what? Oh, these are some great answers, We've got focus, we've got first image of a guide star, we've got took a selfie, aligned the mirrors, consolidated its mirrors, focused its mirrors, all sorts of good answers here. Do you guys know? Ilva and Ron? It's okay. You can shout it out if you know. Reached its home. That's a good one.
I just answered mine.
Oh, you did? Oh.
I actually really don't know.
Oh, that's okay. That's okay. There's been I know you're deep in dissertation mode. So
yeah,
when I was in the last few months of my dissertation, I didn't like talk to anyone. I was just like, I have to type and write the finale of my dissertation. So no worries. Thank you for taking time to do this, Ron. Okay, we've got some great answers. And the question, many of you guys got the question correct. There's actually a few different answers, but the kind of primary one that I was looking for was took its first image. That's also known as first light. It's the first light that goes through the telescope to the detectors. It also did take a selfie, but this is its first image. So all of these different bright spots are in fact a single guide star, a single star. And remember, the James Webb Space Telescope has several different mirror components. All of them are controlled individually. And so the light from those different elements, the light from a single star passing to all those different mirrors, they need to align them and focus them individually, and then they'll put them all on top of each other. And there's a really nice little video that kind of graphically demonstrates this, because NASA cares about us understanding what all of our taxpayer money is going to. So I'm going to play that really quickly here.
So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned, so they actually act like 18 separate telescopes. And we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near infrared camera and we took images in different parts of the sky. And then we looked for the 18 spots from the 18 different telescopes, if you will. And we were very excited to find them. And the 18 spots were actually fairly close to each other. So really everything was very close to what was predicted. We've identified which of the 18 spots is which mirror. At this point, we even know which ones are from the wings. And it turns out one of the wings, you can actually see those 3 spots are a little farther over. And that's sort of what we expected. So we've identified all 18 spots, and the next step is to make an array of them. And then we're ready to start what we call global alignment, which is when each of those 18 spots will start to be aligned and focused. And that's sort of the last step before we take those 18 spots and put them on top of each other to start forming a single star going through the 18 separate telescopes. That's the work that we'll be starting soon. We also took...
Yeah, so I think that was a pretty good explanation. Thank you, NASA scientists, for that explanation. So pat yourself on the back if you got that one correct, everyone. But don't worry about it, Ron. Just finish your dissertation. That's the most important thing for you to do right now. Okay, so a question that's relevant to Ilva's talk. What element from the periodic table is not created by stars of these 6 different options below? Hydrogen, helium, oxygen, iron, lead, or uranium? Uranium. Everyone knows uranium, the one that's radioactive and goes into all the nuclear weapons and nuclear reactors and that sort of thing. Got a few here. Pretty exciting. I'll wait a moment so it can populate a little bit more. But so far, the leader is uranium. Hydrogen gaining, oxygen making a late comeback. And I should be like a horse race. I need to talk faster if I'm going to be a horse race announcer.
One of those auction announcers.
Yeah, I can't do that. Those people, I don't know how their mouths move that fast.
Is it uranium that's used in nuclear power plants? I thought it was like plutonium.
Well, I mean, you have to start with something. You can't get plutonium by itself. That needs enrichment. So usually a lot of nuclear fission facilities will start with uranium and enrich it, I think, to plutonium, and then use plutonium in some capacity. But certainly, like the atomic bomb was uranium 235, isotope 235, as opposed to 238, which is the most common component. So I actually don't know too much about, or probably wouldn't be allowed to talk about if I did know, the various means for enriching radioactive elements to use in weapons and energy production. But all right, so it looks like uranium is our winner here, and then hydrogen, and then lead, and then oxygen. No love for helium. Poor helium. After our helium stars presentation, still no love. So the answer is in fact hydrogen. Ylva, would you like to give a little bit of an explanation for this?
Of course. Yeah, I'm very proud that everybody in the audience realized that helium is created by stars. So there is actually a lot of love for helium. The true answer is hydrogen. Hydrogen comes from, we think, the Big Bang. And that was where most of the hydrogen in the universe was created, and a little bit of helium as well. And so that's why the stars, in fact, the young stars have this hydrogen-rich envelope, because that's what they were created from, the gas from the Big Bang. Now all these other elements, let's see. So we have, maybe I can use some
Here, I can
here. Does it work? So helium, hydrogen here, yeah. Big Bang fusion in blue. Okay.
Oh, perfect. This is great.
Yeah, and the helium, you can see that helium, yeah, much of it comes from Big Bang, but there is the green and the yellow, which is also from massive stars. So massive and low mass stars. Then we have oxygen, predominantly created by stars. What else we had? Lead, that is PB, right? Let's see if we can find that one.
So lead should be, oh, no, I can't. Oh,
this is very complicated. It is. Oh.
Here's uranium down here.
Okay.
At 92.
Uranium 92. So this comes from, I mean, it depends on if you would define a neutron star a star, but I think that neutron stars are stars because they come from stars.
They come from stars.
Right, exactly. And they even shine a bit. They are the lighthouses of the universe, right?
Also, it's called a neutron star.
Star, exactly.
Exactly. Yes. And so somewhere here there is
here's lead.
Oh, there's lead. Thank you. Lead, yeah. So lead is a mixture here of neutron stars and dying low mass stars, and iron we have up there. So iron, most of it comes from low mass stars when they explode, but a bit also from exploding massive stars. So yeah, the true answer is hydrogen. Hydrogen is not produced by stars.
Thank you very much. Okay, moving to our next question. What European-Russian Mars mission is very likely to be delayed due to the Russian invasion of Ukraine that began earlier last week, or late last week? So the European Space Agency and Russia have been collaborating on a number of different fronts, but specifically on a Mars mission that has a rover component that'll zoom around on the surface, similar to Spirit and Opportunity and Curiosity and now Perseverance have been doing on the Martian surface. Yeah, all of them, indeed. Yeah, Ron, in case you're really deep in your dissertation research, Russia invaded Ukraine and there's war going on.
I realized.
Okay.
I realized.
Just to keep you aware of some current events that will be relevant. Okay, so we've got a few suggestions. Vodka one, clever work there, person. ExoMars, Rosalind Franklin, all of them. Yeah, so there are a number of things with all of the embargoes and rules that are being imposed on Russia for this aggression. Russia previously had a number of missions that were being launched out of French Guiana, which is that's the launch location in the northern part of South America, where the European Space Agency launches much of its things, like the James Webb Space Telescope was launched from there. So they're being blocked from there, and Roscosmos, the Russian Space Agency, is pulling out of there as a result. Of course, Russia is one of the partners of the International Space Station, so there's some concern that there may be turmoil aboard or in continued operation of the International Space Station moving forward. Thus far, there hasn't been any trouble on that front, but it may start to become a problem as if this aggression and this warfare continues.
I think there was a YouTube discussion by some former astronaut describing like what a conflict arose, talking about what was happening on the ISS.
Oh, really?
And I think he described it pretty well. Something about how like they're like, you know, there would still remain collaboration with them and everything until they actually land back on the ground, kind of a thing.
I see.
So like everything should be fine up there.
Yeah, hopefully it doesn't turn into World War III in the International Space Station. Somebody pulls out a, AK or whatever, and it's the end. So yeah, hopefully the scientists can continue to operate in a peaceful way despite any kind of aggression that's occurring on the ground. Hopefully.
I trust scientists.
What's that?
I trust scientists.
I mean, I do too, but that's because we're scientists. Like, I trust me.
That's true.
I trust you guys. So lots of good suggestions here. Lemonade. A tasty summer beverage, lemonade. So the answer is indeed ExoMars that was suggested by a few people. This is a map of the Martian surface, of the global Martian surface. And you can see the locations of various landers as well as rovers that have occurred over the last, 40 years. 50 years even. And the ones that are in bold are still in operation. So you've got Perseverance, everyone's favorite Mars 2020 rover that's zooming around, that just arrived last year. You've got InSight, which is another NASA mission. You've got Curiosity, which is another NASA mission. Most of the missions that have successfully landed are in fact NASA missions. They're American missions. Mars, it's hard to have a soft landing that remains operational when you land. There's also, notably, is Zhurong, which is a Chinese rover that's operating on the surface of Mars that landed last year. And then you see here in yellow, Rosalind Franklin, which is part of the ExoMars mission, the joint European Space Agency, Roscosmos, Russian agency, that was meant to launch later this year and then land there. Of course, it's named after Rosalind Franklin being the prominent English chemist and biologist who was partially responsible for the discovery of the nature of DNA, the double helix, due to her work on X-ray diffraction of the DNA molecule. So this was named after her. The rover's named after her, which is pretty cool. But yeah, due to the aggression, there's all kinds of ties being broken with Russia to make it less favorable for them to continue to declare war on a neighboring nation. So it's definitely in danger of not launching on time and maybe delayed into the future. It's a shame because having another rover to zoom around on the surface of the Mars and learn things about, in particular, it was going to be looking for evidence of life and evidence of water and the chemical environment down as far as 2 meters below the surface. It was going to have various means of checking things out. It's a shame that it probably won't launch on time. So we'll see. Was
So,
your
so
question,
do you know how much it'll be delayed? Like, is it 5 years, 8 years, or something? Like, don't they have to get it like some
what I read, the
optimal.
next launch window that would be available if they don't make the August or September 2022 isn't until 2024. That would be the next window.
Okay.
And then, of course, it takes about a year to actually get there because Mars is not just like I throw a baseball and it lands on Mars. It's like a year away. So
there's like a whole delta V optimization calculation you got to do.
Exactly.
Yeah, all that. Yeah.
So, oh, and here's a nice little picture. Hey, guy, what's going on, ExoMars? Hey, Rosalind Franklin, what's up? So that's nominally what it would look like if it were taking a selfie on Mars. Cute little guy. Okay, astronomers have discovered galaxies lacking what component thought to be present in all galactic systems, thought to be a requisite of all galactic systems. There's this was initially kind of discovered with some trepidation, with some hoopla in 2018, but there have been notable additions to this whole epic over the last few years. And in fact, there was a paper released last year that I'm a co-author on. That's partially why I chose this, because I was pretty psyched about it, that I'm a co-author on. I mean, I'm just like an nth co-author, so I didn't do a lot for the work, but it's it adds to the whole saga of what this means. So astronomers have discovered discovered galaxies lacking some component that we thought was necessary and present in all galactic systems. So what do you guys think? Lots of pants. Galaxies without pants. You heard it here first, people. Astronomy on Tap, Los Angeles. Galaxies without pants. A massive black hole. Dinosaurs, aliens, stars, the Borg. Supermassive black hole. Mathematical abomination. I like that. William Shatner. Not found in every galaxy. Dark matter. Indeed, the answer is dark matter. So this galaxy, there have been a few discovered thus far, the first of which was in a famous Nature paper by Peter Van Dockum and collaborators. Peter Van Dockum is a professor at Yale University. I think, yeah, like I said, I think this paper came out in 2018, but I'll kind of give you the saga of this whole business. So this is a galaxy. It's a low mass galaxy. It's not nearly as massive as our own Milky Way, although it is nearly the size of our Milky Way. And you can see it's pretty see-through, right? When you look at it, you can see these other galaxies. These are background galaxies behind it, but we can see them because the galaxy is pretty sparse. It's not very densely packed with stars or other stuff, which is already kind of weird. It's considered an ultra diffuse galaxy. Diffuse just meaning like sparsely, not very compact. And if you zoom in, you can see the individual stars that are present in this system. And what you'll notice, if you look, and what this paper did, was it looked at the speed at which all of these little stars are traveling around. And they're flying around all over the place, as stars tend to do in lots of different galactic systems. But what that implies, if you look at it, is that in general, if there's no force that prevents those stars from just continuing to travel in their direction that they're going, then the galaxy itself will just fly apart. That's generally that's the justification that we have. It's called velocity dispersion, but it's just the tendency of stars to move around within a galactic system, or any real system for that matter. But in a galaxy, they move around, and if unimpeded or unopposed, they'll just fly apart. And so the thing that opposes that and prevents them from flying apart is the force of gravity. Everybody knows gravity. It's the thing that holds you onto the Earth, but it's really just an attractive force where any two objects that have mass are pulled towards each other, like these stars. These stars are pulled towards each other because gravity attracts them to each other. And so gravity opposes that velocity dispersion. It prevents those stars from flying apart and kind of disbanding that galaxy. Now, that's the justification for dark matter, in fact, is that if you add up all the stars and gas that are present in most galaxies, like the Milky Way or the Andromeda Galaxy or the Large Magellanic Cloud or any of the galaxies that we see in the universe, you need some unseen mass that's there that's imposing its gravity to hold the galaxy together so it doesn't fly apart. But what's interesting is that this particular galaxy, you don't need that dark matter there. If you add up all the mass from the stars and the gas, it's enough to keep that galaxy together. And so it looks like there's no need for dark matter and there's no presence of dark matter in a couple of these different galaxies, which is kind of wild. Yeah, so the galaxy doesn't require dark matter to hold it together. And when this paper came out, people were like, oh, this is crazy. We need dark matter. We have to have it. Not trying to say that we don't need dark matter in all galaxies, but there are a couple of galaxies that have now been discovered that don't seem to have any dark matter in them. Now, the paper that came out last week, where the first author, the main author of the study, his name's Jorge Moreno. He is a professor of astronomy at Pomona College. This is a plot from that paper. We conducted a series of computer simulations because that's what I do. I do computational modeling of galaxies. And we found that there were some galaxies present in the simulation that also lacked dark matter, basically having a theoretical justification for the observations that Peter Van Dokkum and collaborators found in the last few years. So it adds to the possibility that this is in fact, this is in fact a reality in our universe. So on the top 5 plots in black, this is what the starlight looks like from these systems. So you can see like there's some galaxies here, and then there's galaxies in these circles. And then on the bottom, it's just showing the mass distribution, the dark matter distribution. And you can see, oh, look, these guys here that have a bunch of bright starlight, they also have a bunch of dark matter present in them. But look at these guys. That guy has some stars in it, and there's no dark matter in it. And so, yeah, it's just kind of, it's an interesting result that seems to suggest that simulations, in fact, can reproduce the fact that there are some galaxies in the universe that don't have dark matter in them as well. The reason that they don't have dark matter is because these particular galaxies had a really, they're satellite galaxies to the kind of main galaxy in the system, and they passed so closely to the main galaxy that it like stripped out, it pulled out their dark matter, and it only left the stars in the center. So it's not a very common thing that happens, but it does seemingly happen. But stay tuned. This is definitely a field of research that's interesting, and a lot of people are working on. So maybe it'll change one way or another as time unfolds.
So
Okay.
a quick question.
Yeah.
Quick question on that thing. So on in the simulation, are all those like the ones that don't have dark matter? Are they all light galaxies?
Are they all what? Light galaxies?
Yeah. Like are they not very massive galaxies?
Yeah, they're low mass galaxies. They're all
okay.
They're all satellite, like dwarf galaxies. So on par with, I think they're even lower mass galaxies than our Large Magellanic Cloud and Small Magellanic Cloud. I think they're more like some of the like Leo and some of the dwarfs that are orbiting around Andromeda or the Milky Way. They're like 1/1000th the solar the mass of our own Milky Way, something like that. But they're also consistent with the observed one, that they're these ultra diffuse ones that are really spread out instead of being compact. Anyway, next question. How many official constellations are there in the sky? Yes, constellations are dumb. Well, they serve a purpose. You don't have to interpret them as being your astrological sign. You can just use it for identifying a location on the sky. I mean, that's what we do as astronomers. Like, constellations serve a purpose in the same way that if you came to the Earth and you'd never been to the Earth before, and let's say I wanted to say, I live at a particular place on Earth, I might start off and say, I live in this city, in this state, in this country. And those are all demarcations of a spherical distribution. So Ylva, what part of the world, where were you born?
I'm from Sweden.
So by Sweden, you tell me exactly, there's some region of the surface of the Earth from where you come.
Indeed.
Indeed.
Yeah.
So similarly, we could say, where is that star? And the first thing that you might say is in Ophiuchus or in Virgo or in, Ursa Major or something like that. And it's just a division of the sky into a little chunk of space. And I don't have to think of that as the Big Bear or the snake charmer. I can think of it as, or no, snake handler. Ophiuchus is the snake handler, right?
There is some fun things too, like Cygnus, for example, has a lot of black holes.
Oh, is that true?
Yeah.
I think of Cygnus X1, but I didn't realize there were a bunch
There
of
is also Cygnus X3, so also X-ray binary. And that one has a Wolf-Rayet companion, so it's probably a massive helium star.
Oh, really? Oh, okay.
Yeah, so there's it's a fun way to think of the binaries. Like Beta Lyrae is in Lyra, of course.
Of course.
Was it X1 or X2 that was that famous one among relativity?
I think
The
X1
bad
is
place.
famous, no?
Yeah, I think of
Cameron,
Cygnus
maybe
X1. Isn't Cygnus X1 one of the brightest X-ray sources in the sky? I thought it was like, but
I think that was the one where they're saying it was like like most relativists were saying like, oh, that's evidence for black holes. It's either X1 or X2. I forget.
I think it's X1. But
I don't know. You're the black hole guy, dude. I don't know. I know galaxies and
that's so long ago. That's like 70s. That's like 80s or something before I was born.
Very good point. Depends on the culture. Different cultures have defined their own constellations. Absolutely. Constellations are dumb. Yeah, kind of, but useful. Who's cosmology? Okay. 538. Let's 1342. Let's not go crazy here. 11D. Very, very solid. 825 on weekends. The answer is indeed, at least in the officially recognized Western constellation set, 88 is the modern constellation number. Here's kind of a map of the entire sky and this constellations. I guess I should have applied a map that shows the boundaries of the constellations as opposed to the stars that kind of define them. And of course, you have to be quite creative to see what each of these are supposed to mean, right? So you've got like, let's find one. Draco. Does this look like a dragon? It's a bunch of stars in a windy little line. Looks kind of like a snake the way it's. Ursa Minor. Does that look like a little bear? No, not really. Ophiuchus. Is this a snake handler? Not so much. The only one in my mind that really looks like what it's supposed to is Orion.
Yeah, I was going to say that.
Where is Orion? Oh, it's over here. You've got like the belt and the shoulders. And no, I guess these are the shoulders and these are the knees. Can't tell if it's upside down. Oh no, these are the shoulders. That's Betelgeuse. Gemini, two twins. I don't know. Anyway. Yeah, so the answer is 88. So good job for those of you who said something clever. How many U.S. national parks and monuments are official dark sky parks? National parks, a lot of them have their motto of half of the park is after dark, because you go to these natural places, you look up. They're usually in kind of remote locations, not all of them, but many of them are in remote locations. And so they're far away from towns. They don't have a lot of light pollution, and you can look up in the sky and have a really nice view of the heavens. I was actually just at one this last weekend. We were holding we were helping organize the Dark Sky Festival at the Death Valley National Park, which is a very nice place to go and observe the skies there. And I think there were a few thousand people who showed up. There were lectures, there were science demos, and then we brought telescopes and got a chance to show everyone nice views of the sky. So I encourage people. There are other dark sky festivals, some that are held by the Grand Canyon, Sequoia Kings. I think Great Basin does one, Joshua Tree does one. So I encourage people to check them out. Super fun, free. You get to learn about the sky. You get to look through a telescope. And even if you don't look through a telescope, it's just awesome. You look up, you see the Milky Way, you see all these stars that you can't really see from a city or even a suburb. Super cool. So lots of where is us? Oh man, I wish I could tell you. That is where is the US? How many United States? I guess I should have been more explicit there. I prefer where is us, really. That's the deeper question that I think we should all be asking ourselves. Right.
I think another thing I'll add on to most of these like parks is that you usually have the Bureau of Land Management camping sites where you pay like $20 to sleep there.
So, well, I mean, BLM, Bureau of Land Management, you can roll in and just camp for free anywhere. That's the great part of BLM. Yeah. These are national parks or national monuments, but they're run by the National Park Service. So that's how they get designation. So the answer, I do see the answer. Oh, pi, very clever, very clever. 40. That I'm going to be thinking about that one for a few days. 40. The answer, in fact, is 27. Here's a nice little map showing their distribution. You can see they're primarily clustered around Arizona, Utah, Colorado, Nevada, simply because that's where the people aren't and the cities aren't and the lights aren't. But there's a few other ones here. You've got this one in West Texas, Big Bend. Really good skies, evidently there. I forget that I thought that was Everglades, but it's not the Everglades, but it's in southern Florida. It's a national monument that's there. Katahdin Woods in Maine. You've got Glacier up here in Montana. Here's Death Valley. Yeah, Death Valley. Here's Joshua Tree. Woo! Close to Southern California. So anyway, really cool things. And as I said, yeah, like here's a nice one from Joshua Tree with a Joshua Tree. Nice view of the Milky Way. If you haven't had the opportunity to look at the Milky Way, go to a place where you can look at the Milky Way. It's really a special experience. And some of these national parks can provide that. And they have rangers who will be able to tell you all about the mythology associated with different astronomical origin stories, as well as the science behind many of these things. So yeah, as I said, we were just at the Death Valley Dark Sky Festival. I think it happens annually in February before the park gets super hot. You don't want to go to Death Valley in July. It's 135 Fahrenheit, like 57 Celsius. That sounds horrible. I don't want to deal with that. Anyway, next question. Ooh, a question for Ron. Total mass of binary black holes do not add up after they merge. Where does the mass go? Where does it go? We've got a few different options. The black holes shrink, so does their mass and size. Black holes don't shrink, it's taken from the total energy. The mass goes because GR is just nonlinear. You can't add and subtract in the ways that you think that you can. It doesn't work. It's nonlinear, people. We don't know, or all of the above. What do you guys think? What do you think? People seem confident here. Black holes don't shrink. They don't shrink, people. Okay. All of the above. Nice. That's a little mix up. Which one is the one? Man, I shouldn't have had 2 hop slams. This is really affecting me. Yeah. All right. Seems like the general consensus is that black holes don't shrink. It's taken from the total energy. Ron, would you like to explain to us?
Yeah, okay. So for the most part, like if someone answered because GR is nonlinear, it's kind of the same thing. So black holes don't shrink, like their mass stays the same, but mass is correlated to the size of the black hole, to what we call the short-trail radius. So what's happening is that we sort of see the total mass, I guess, like of the 2 binaries, because we're seeing the total energy of like both the black holes as well as the orbital energy. So what's being radiated away is the orbital energy. So when it combined, it's actually a lot like the final total mass of the black hole at the end is a lot smaller, because what's radiated away is the total energy. The orbital energy is taken away from the system. And the reason why the total orbital energy is taken away from the system is because GR is nonlinear. So I would say those 2 answers are equivalent in a way. So I would accept both of those. And it's kind of funny because most upper level undergrads or like first year grad students are always confused by this process. They're just like, wait, what? The size of the black hole is determined by the mass. They're just like, but when it combines together, there's like, where does this like 3, 5, 8 solar masses go? But it's like you have to kind of think it like in a more GR perspective, you know. But yeah,
the orbital energy is a significant component of the overall energy, not just the rest mass energy of the system.
yeah, exactly. So you have orbital energy and you have rest mass of the black hole. So if the black holes were isolated, you would measure them like the total mass of the system would be separate. Like if you just take 2 black holes that are finally separated away, it'll add up like if you were to just like sum the 2 black holes together. But when in a binary system, it's not just the rest mass you have the orbital energy. So
how much of that energy is lost from the gravitational radiation? Is it just like a minute fraction?
Not a minute fraction. I think it was the one I showed you was like I think it was 85 and 66. Was it?
Yeah, I think so.
Yeah. So it's so like the one with the whole like the more intermediate mass black holes was 85 and 66. So it'd be 151 solar masses would be if you just like sum them together, just quickly without taking into account the orbital energy. So and then what that is 142 in the end was the final mass formed. So you just take 151 minus 150. I use calculators a lot because I'm afraid of getting things wrong. So that whole process is 9 solar masses and everything. So that's radiated away, like worth of orbital energy.
I see. Okay.
Yeah.
Interesting. Excellent.
And
okay, cool. What do you want to add to that?
Oh, I was saying, yeah, the energy, like when you say it's equivalent to 9 solar masses, you just think of the E equals MC squared kind of a thing. That's sort of how you can sort of like estimate that.
Okay. That makes sense. In the same way that during the nuclear fusion process, this hydrogen atom and this hydrogen atom to make, helium or whatnot, there's some amount that's radiated away in the form of a gamma ray or whatnot. And so mass is converted to energy.
Yeah.
Got it. All right. All of Mercury, the planet Mercury, all of Mercury's faculae, which is just a fancy Latin word for bright spots, are named after what? Some sort of what theme? Because different planets have different naming schemes associated with this and that and the other. Mercury is pretty interesting. I really like this. So that's why I chose this particular question. I don't expect anyone's going to get, Disney princesses, an excellent suggestion. Poets and writers, angels, focus, fungus. It's all named after fungus, different mushrooms, delicious mercurial mushrooms. Some good suggestions. I really wish that there were a planet discovered. Maybe when they discover Planet 9, when Mike Brown and Konstantin Batygin are successful, we can make it so like every mountain on Planet 9 gets named after a Disney princess. I would really dig that. That'd be so great. You've got like Ariel, and you've got Belle, and you've got.
Don't do that. Disney's owning everything already.
Yeah,
plus
that's true. They're
going to copyright. It's copyrighted.
They copyright Planet 9. Yeah, that's probably. You're right. Let's see. Illnesses. Ooh, dark. Caltech astronomy students. Nereids, women, fire, snakes, kicks. How many kicks are there? There's like the drop kick, there's the side kick, not so many kicks. Couldn't have a lot of.
Think of all the different martial arts that I guess they do.
Leprosy variants. Oh, yeah, I dig that. The answer is indeed snakes. It's words for snakes in different languages. I think this is amazing. And the reason Mercury is wild, right? So you've got mountains that are named after different words for hot or fire in different languages, which is pretty sweet. But yeah, these bright spots, these little guys here, boop, boop, which are just, high reflective locations on the surface, presumably due to upchurn of material after an impact or struck, overturning the regolith and making it bright in that region for some period of time. they're all named after snakes in different languages. So snakes, of course, because Mercury, the god, was like the messenger of the gods, and he has this little staff, caduceus, I think is the word for it, and it has these snakes. Woo! And it's like the modern medicine symbol and all of that. Like if you, I don't know, like International Red Cross has like the snakes and the caduceus with it. But anyway, so that's why it's chosen to be snakes. But yeah, look at the Wikipedia article. It's like these different things are named after the Somali word for snake, the Quechuan word for snake, the Malagasy word for snake, the Fijian word for snake. And so I think that's pretty creative, pretty awesome. Anyway, good job, person who got snakes. I hope you knew that answer and you didn't cheat and look it up on Wikipedia. Finally, I think our final question for the night. Mimas, a moon of Saturn resembles which object from science fiction lore? Who knows science fiction and who knows Saturn? Interstellar, interesting. Death Star, whoa. Death Star just got big. The Eye of Cthulhu. King Midas. Midas sounds legit to me. Bigfoot. Bigfoot is indeed an object from science fiction lore. Sasquatch of the science fiction lore. Mr. Meme, that's no moon. Potato. Yeah, a lot of asteroids do look like potatoes. A lot of moons look like potatoes. All right. The solar system. Indeed, the answer is, in fact, the Death Star from Star Wars. Here's a nice comparison image. So you've got the Death Star from the popular science fiction franchise Star Wars on the right, and then you've got Mimas, this moon around Saturn with this enormous crater on its surface that looks a bit like the Death Star. So indeed, this crater, whose name is Herschel, because Herschel was the person who discovered this particular moon. Herschel was also a famous observer. He was the first person to discover Uranus, the first like modern planet that was discovered that hasn't been known since antiquity. And yeah, there's this enormous crater. It's like a third the size of the diameter of this whole thing. If such a crater, like proportionally sized, were on the Earth, it'd be the size of like Australia. It's this just enormous kablam that struck this thing. And in fact, the impactor that created that crater came very close to destroying the entire moon, because obviously it gets much bigger and you're just going to destroy the entire moon and knock it apart. So yeah, pretty cool. Oh, that's the end of our presentation. That's the end of our
It could also just be an abandoned Death Star.
It could be. Hopefully they
just
don't
hit by craters.
They just left it idle. They were like, oh, we ran out of batteries. Let's move to another system.
The Empire has fallen. Let's abandon ship.
Cool. Well, I guess we're a little bit early, but I'm tired and I still have to finish my second hop slam, which is pretty strong. Speakers, thank you very much. Ilva, Ron, excellent presentations. Thank you for your contributions and dealing with my ridiculous questions and the questions from our audience. I really appreciate you guys taking your Monday evening to and the glorification and the education of our viewership. Thank you very much.
Thank you. It was great to join.
Yeah, sure. I love this. I just get a chance to drink beer and talk about science and learn a bunch of stuff. So it's super fun for me.
It was a nice way to take a break.
Yeah, you need to get back to that dissertation. Thank you to our audience for taking time out of your day or your evening to join us tonight. And thanks for the participation and some of the clever answers for our pub trivia. I got a chuckle out of many of them, so thank you very much. And our next event, as I mentioned at the beginning, our next event will be a stargazing lecture this Friday the 4th of March, that will be again drawing similar science but different focus on binary stars, on interacting binary stars. Woo! from a postdoc and a National Science Foundation prize for postdoc in Caltech's department, Margaret Lazzarini, who will be joining us. And you can find it on YouTube. I'll also post advertisements for that shortly. And then our next Astronomy on Tap will be in 2 weeks' time on March 14th. And I will be posting information about that soon. But we have these once a month. There are the stargazing lectures that happen once a month, and some other, cool events. We're actually, in the next couple of months, going to have one that's on the science of Star Wars and the science of Star Trek. It'll be a battle to the death of the galaxy. So I'm really excited about that one. That should be fun. So thanks everybody for joining us, and I will see you guys next time. Thanks, Ilva and Ron, once again.
Yeah, sure.
Thank you.